Okay, everybody, these are some differentiability examples I promised I'd try to get up for you guys this weekend here. And so let me kind of look at a question here. I'm going to number them. So maybe in the future I'll make a worksheet, but so we're going to number them and we're going to say here's a function and it's going to be, let's say the absolute value of x plus 2, and they want to know at -2. So here's going to be the question here, right? They're going to say to show the function f is discontinuous. All right, show the function f is discontinuous. And it's going to be at the point a being -2, or you can say x being -2. Okay, so let me get that down here. So show that the function is, and I apologize, I haven't had all my coffee, is not differentiable. Ooh, discontinuous. The function is continuous. Sorry about that. Show the function f is not differentiable. Okay, now let me point out to you something we talked about. This function here is essentially the absolute value function. But if we go to Desmos and I say, okay, Desmos, let's add a curve here. We're going to add y equals, and maybe we have the function over here. And we're going to have inside here x plus 2. That's the absolute value function here, okay? So as you can see here in Desmos, at -2, you have a problem. It's not smooth. So we have a corner, ladies and gentlemen. An abrupt change there in the curve happens at the point -2, or the x value or a value at -2 here. So you have a corner. And as we know, at corners, our functions are not differentiable. So when you look at this question, it makes a lot of sense, right? They're saying show that the function is not differentiable. Now, showing that a function, this word here, so that you guys know, show, we look at as maybe possibly, right? Not possibly, but we show this as proof. So sometimes you'll see the phrase prove that the function, okay, is not differentiable. And we know that. We looked at the graph. Now, what I mean by showing, you don't just do this like on a task. You don't say, here you go, Mr. Judge, I just showed you. It's not differentiable, right? You guys know what I'm talking about? Showing a graph is not good enough. To show, you have to prove. And you might say, well, how do I prove? You prove by using the definition. So we have the definition, f prime of a is the limit h goes to 0, f of a plus h minus f of a over h. We use the definition. And you might say, well, okay, well, how do we use this definition in this case? Well, this is one definition we can use. We can write down the other. However, let's try this out. Let's try it with this. See what happens here, right? So a is -2 here. We got -2. And make sure we're going to show here that f prime of a, we're going to see what happens with this. If it's not differentiable, just so you guys know, what we're really trying to show is that this limit, right, does not exist. This is the exercise by using the definition. So when we're trying to find out whether this is differentiable or not, that's what they're asking us. Show that that limit does not exist. And so we have that limit as h goes to 0, the absolute value. Now you're going to plug this in. Be careful here, right? Be very careful. I almost fell into my my trap there, right? You're going to plug in -2 plus h for x, right? Wherever there's an x, you plug in -2 plus h. So you end up with the absolute value, -2 plus h, and don't forget there's a +2 here, right? You're looking at this. Now that's going to be f of -2 plus h. We also need f of -2. And you say, how do I get that? Well, plug in -2 there now. And so you'll get minus -2 plus 2, everything over h. So we're using the definition. And at this point, you say, is this the limit? H goes to 0. You get the absolute value of h by combining like terms minus 0, because these terms here, -2, +2 cancel. This is 0. So ladies and gentlemen, there we go. And don't forget we're dividing by h here, which is really the limit here. H goes to 0. Absolute value of h over h. Now, this is what we have to really look at in detail. All right. And this is actually a question. Oh, I should say, I gave you a similar question like this on your test where you had to find the limit of the absolute value here. And we showed that that did not exist because we're looking at h going to 0. So we have to look at the approach from the left and the approach from the right. So we already know what that is. And I'm going to say to you, I want you to recall, I'm going to define it this way, right? This function that we have to take the limit for, let's define it piecewise. It's h over h for h greater than 0, right? We can't have 0, and that's okay. We could look at it this way because we're looking at the limit as you approach 0 from the left or the right. And that happens when my h value right in here, right, is positive. And you say, well, what happens if the h value is negative? Well, you say minus h over h for h being negative. Okay? Now, the thing you want to remember, and I'm sure you guys do because you did pretty good with this on your test, that, you know, when you have h being positive, you're approaching 0 for those positive values. You're approaching from the right. So that's right-handed limit around 0. And when h is negative, as you approach 0, you're approaching from the left. So this is the definition of the function. Now, you might say, Mr. Judge, I know h over h, right? And that's a 1. And you're right. And you know minus h over h, that's a -1. Absolutely. So we can replace here these values. And so what you see now here is the limit. H goes to 0 from the left of that absolute value of h over h is going to be -1. While you have the limit here, h goes to 0 from the right, that absolute value h over h, which is really +1. And we can actually just use those values, right? Because it's a constant. +1, -1. So this is 1 here. So we're just using this information. And you guys know that these numbers are different, right? These limit values are different. And because they're different, you know that that limit does not exist. So you say the limit, h goes to 0. And you might say, a limit of what? Well, it was the limit of this whole thing to begin with. And I guess we can say the limit as, first of all, the absolute value of h over h does not exist. Let's kind of complete this, which really means f prime at -2 does not exist. That limit does not exist, right? And that means your function f is not differentiable at x or a is -2. So essentially, this is the proof behind this. This is the whole idea. They want you to see this limit not existing, and it's going back to the definition of a limit, ladies and gentlemen. Definitions are everything in every topic. Don't shy away from them. They're here for you to learn about them. So, you're trying to find whether this limit exists or not, right? And existing means finite. Not existing is either infinite, positive infinity, negative infinity, or you guys know the meaning of does not exist, right? The two values are not the same. Anyway, notice this is what we just showed. So here's kind of a classic question. And I'm going to say something, I'm going to make a remark, by the way, right? I can call it by the way, or I can call it another question. Maybe we'll say two, just to really emphasize. I know it might seem not necessary, but I think for some it is. We're going to change the a value. I'm going to say at the origin, right? And now we're going to say show that f is differentiable at, if you want to say a is 0, you can say a is 0. At the origin, right? So we're going to look at this curve. And you say, well, where's the origin? The origin is at really when a value is 0, the y value is 2. So we change the, don't even look at the corner there, right? At the origin, the curve is smooth, ladies and gentlemen, meaning there's no abrupt change in direction. I mean, a seriously abrupt change. So the slope of the tangent line doesn't change dramatically there, right? It's nice and no change, actually. There's no change in that derivative, and that's kind of what you're looking at. Derivatives change, ladies and gentlemen, but how abrupt do they change? When a is -2, very abrupt. But when a is 0, not abrupt at all. So that's going to be differentiable. Now let me show you. Because it comes down again to, when you say this, what do they mean by this, Mr. Jubb? To show? They mean to prove. And you say, what do I have to prove? You're going to have to prove that f prime at 0, is finite. Some finite value at 0. I mean, that's what they mean. They just mean check your definition. So you say f prime a, which is the limit now, h goes to a, f of a plus h minus f of a over h. So I'm going to check at 0. A is 0. Okay? So when we plug in 0 here, we just simply get the absolute value of 2, which is going to be positive 2. So this happens when we're finding here, right? You can say, hey, that's the absolute value of 2. Okay. 0 plus h, right? And notice what that gives us here. 0 plus h, let's get the right color. That'll be absolute value 0 plus h plus 2. Everything's over h, which is the limit here. H goes to 0. Absolute value h plus 2 minus 2. Everything over h. All right, let's double check something here. See if we're okay. Put in 0, we got absolute value of 2, and then you say, okay, 0 plus h there. So it's the absolute value of h plus 2. And we're going to have to take this limit as h goes to 0 here. And so if we start off now and we say, okay, let's plug in that 0 here for h. Notice this, we get 0 over 0. So we can't just plug this in at this point. It's indeterminate. So at this point, it's not a trick question, but it does test you on some very serious fundamentals. Meaning, what's going on in this situation? You guys know you're going to have to use algebra here, right? So the idea now is to use algebra. And we say, well, how can we use this algebra? We have an issue with algebra, or do we? I want you to note something here, right? And I'm going to paint this green. I'm going to say to you, what are you looking at here? What's that definition, right? The definition of the absolute value of h plus 2 is h plus 2 when h plus 2 is greater than or equal to 0. It's opposite h plus 2, right? When the h plus 2 is less than 0. Remember, this is a piecewise function. Okay? And you go, Mr. Judge, h can't be 0. Okay, we're going to throw out the 0. I mean, this function can have this, by the way. In terms of the limit, you can't have 0 there, but this function can have 0. So I'll let you guys know, we're just looking at this particular function in green. Okay? Now, here's what I'm going to get at. If you use some algebra, this portion here on the right, using some algebra here, this means h is greater than or equal to -2. And this means h is less than -2. This here is the key. And you say, why is this a key, Mr. Judge? Because take a look at your limit question now, right? H here, let's get the right color. H is going to 0. So that means h is around 0. That's the key. So if h is around 0, let's ask you, here's the top function, here's the bottom function, right? The values of h around 0, we get to use let's double check, let's read this correctly. We get to use, ladies and gentlemen, the top here. And you say, why do we use the top? Because we use the top function when h is greater than or equal to -2. The bottom function is used when h is smaller than -2, right? I mean, I don't know if you want me to look at the real number line. If you had to graph this, right? We say here's 0, -2. So the top function is used for these values of h. So around 0, ladies and gentlemen, that's why we're using the top function. Okay, this is my point here. This is for the top function. It's just h plus 2. So we can replace this with an h plus 2 because that's the definition. So we get the limit, h goes to 0, h plus 2 minus 2 over h, which is the limit, h goes to 0 of 1. Because when you combine like terms here, the 2 and -2 cancel, meaning it's really 0, and then h over h is 1, ladies and gentlemen. So this limit here is, sure enough, limit of a constant is the constant. This limit is 1, ladies and gentlemen. And that number is, by the way, finite. So what you showed here is really f prime is 0 is 1. This is a finite value. That means f is differentiable at a being 0. Okay, so here's the idea behind it. I know it seems trivial to some, but for some people, they need to see this. They need to compare and contrast. And that's what we're doing here for some of these. And so I think it's a pretty good question to look at. Anyway, and it's all about looking at that curve, smoothness, okay? Because at these points, the curve is continuous at 0. Remember, differentiability implies continuity, not the other way around. So if it's differentiable at a point, it's continuous at a point. Okay, let's look at another example. We'll call this one 3. And this example is a piecewise function. X, absolute value of x, for x greater than or equal to 0. And I think it's minus x, absolute value of x, for x less than 0. They're going to say, show f is differentiable at 0. I think this is what it is. Let me double check. I'm not sure where I have this. I have it in my notes somewhere. All right, I have it in my notes. Now, remember, we've been saying here, if they ask you to show, what that means is to prove. And now you have here f prime at 0, limit h goes to 0. F of 0 plus h minus f of 0, everything over h. Now you say, can I just start off with a, and I'll say okay. And they want you to show that this thing is finite, some finite number. Right? This is what they want you to do. Okay, now what we're going to need to do now, ladies and gentlemen, is the following. We're going to have to get our handle on this. So I guess if we plug in, if we start to do this, we say 0 plus h, right? Here's what we started to do. Right, you have this 0 here. That just leaves you with h. I mean, I'm going to do it this way. This isn't b. F of 0 plus h minus f of 0, everything over h, limit h goes to 0. Let's get this out of the way. Okay, and then you say to me, but we have to know what's going on with this function, right? You got the absolute value here. Now, let me show you what this function really is. So I want you guys to notice something here, right? Even though they said f of x is x, absolute value of x, and I think I have this. Do I have this right? I might have a typo. Yeah, I apologize. Apologize for you. I do have a typo, but that's okay. If I find it, it's not a mistake. Here's the function. And here's your function. Show f is differentiable at the origin. Okay. So we're here. And let's see what this means here for us. Okay, so we can plug in the 0 and we get that 0. We plug in 0 plus h. All right, that's going to change what we see here. So we're on our way. I apologize. I misread this. So limit, ladies and gentlemen, h goes to 0. H, absolute value of h, minus 0, absolute value of 0. Everything over h. All right, it's not going to be so, this might be the easiest question of the batch here. And did I make a mistake? 0 plus h. Well, 0 plus h is h, so you're good. Okay, so we have h, absolute value of h, minus that 0. Let's just say it's gone. over h, and ladies and gentlemen, you got the limit. H goes to 0, absolute value of h. I'm going to write it down here. So let's talk about this. Kind of interesting. All right, ladies and gentlemen, you might say to me, Mr. Judge, is that the absolute value of 0? And I'll say yes. And you say, why? Because remember the absolute value function? Right? It's continuous at 0. It's actually continuous everywhere. So we can simply say, oh, that must be equal to 0, which is finite. And it is. So what we have shown, ladies and gentlemen, is that f is differentiable at a is 0. In fact, what we showed was f prime of 0 is 0. 0 is a perfectly acceptable finite number. Okay? So at the origin, the derivative is 0 here. So that's pretty interesting. Now, let me show you the essence of my confusion here, ladies and gentlemen. Let me show you why I wrote it down correctly, because I looked at it incorrectly, but nevertheless, let's show you what's going on here. What's the definition here of this function, right? Absolute value. This is x times x for x greater than or equal to 0. This is x times minus x for x less than 0. This is really x squared when x is greater than or equal to 0. And this is minus x squared, right, when x is less than 0. So as a graph, if you said, I want to see this graph, here's what I'm graphing. When x is greater than or equal to 0, it's just the x squared term. It's a piecewise graph, right? When x is negative, it's opposite that. It's reflected about the x-axis. So essentially, it's a parabola. And it's a parabola that opens up. It's the most fundamental curve you should know on that worksheet. Curves every calculus student should know. So here's my, essentially this is the x squared curve. But in gray, the positive values, including 0, are represented here. But for those negative values we talked about, they need to be reflected about the x-axis, which means that reflection looks something like that, okay? This is the minus x squared portion of it. And then I guess this portion is not there, okay? So what they're saying here is the derivative here at the origin, we'll find out geometrically speaking, that tangent line has a slope. They're saying m tangent is 0, which really means the tangent line is a horizontal line, but we're going to talk more about that issue. But, I just wanted to show you all the gory details. It is differentiable at 0, and since it's differentiable at 0, that implies it's continuous at 0. Beautiful, beautiful, beautiful kind of question this morning. Okay. And I wanted to go through as well another example here, right, where they can say, I guess this is question number, I don't know, where we're at 4. They can say things that you're going to let this function here be x to the 1/3 power, right? And you guys know that's really the cube root. So maybe let's write it that way. X is the cube root function. We want to show f is differentiable at the origin. Or is it? I'm going to show f is, I believe, not differentiable. Okay. Let's look at Desmos. So I want to show you guys something interesting about the curve here. Y equals, where's the cube root? Do we have one? No, I was going to say x to the 1/3 power. Okay, you guys can see that in green. Notice the function's continuous at the origin, but you do have an issue at the origin. We're saying they're asking us to show that it's not differentiable at this origin. Okay, that it's not differentiable. What does that mean, not differentiable? It's continuous at the origin, not differentiable. Let's take a closer look at this. Now, we did something similar in class here, but I really wanted to do this one. This is when I said to you guys, this is where you have a vertical tangent line. This is the example I wanted to do. Okay, you have a vertical tangent line, which means you're going to have an undefined slope. But anyway, let's put this all together. So as you say, you know, f prime at 0 or f prime of a is the limit h goes to 0, f of a plus h minus f of a over h. Okay, you're going to plug in the 0 here. And you say, I kind of know what happens here. We get, you know, f prime 0, limit h goes to 0, f of 0 plus h, which is f of h, minus f of 0 over h. And you say, can I just change it to f of h? You can, right? So here's your function. Plug in h, and yes, you get h to the 1/3, right? Limit h goes to 0, h to the 1/3 minus, plug in 0 now. So what happens when I plug in 0? Well, you get the cube root of 0, and ask my intermediate algebra students, they know that that's 0. So, you know, 0 divided by h. And you have the limit now, h goes to 0, h to the 1/3 over h, and really h to the first power here. So you're going to use properties here. H to the 1/3 minus 1, right, which is 3/3, and h to the minus 2/3. Limit h goes to 0, 1 over h to the 2/3 power. And this is my f prime at 0, ladies and gentlemen. Now, let's stop and think about this, right? Because you're going to 0 here from the right and the left. So if it's 0 from the right, because this is a two-sided limit. Limit h goes to 0 from the right of 1 over h to the 2/3, which means, you know, h is small. So can you say, okay, this is a small number, and it's positive because it's from the right here. So when you actually take a small number and you square it, right, it makes it positive. You take the cube root. What I'm saying here is when you plug in this h value for a small value, this is positive. But it's small. It's a small positive number. So you got this kind of idea of 1 over a number that's getting, this is getting smaller. And you say, what does that do? It means the reciprocal is getting bigger. And you say, well, what does that mean? That means that this is going to infinity. So the smaller h is, the bigger the reciprocal is, right? And I can write it this way. Here's how we formally say h to the 2/3 is going to 0, which means the reciprocal of 1 over h to the 2/3 is going to infinity. This is the logic behind it, right? That term in the denominator is getting smaller, 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 and smaller, which means the reciprocal is getting so big it's without bound. That goes to infinity, ladies and gentlemen. This is the right-handed limit. The left-handed limit again. H goes to 0 now from the left of 1 over h to the 2/3. Now we can say values to the left of 0 are negative. So h will be like a negative 0.001. It's negative. And the second we square it here, right? Because that's really a 2/3 power. We're going to square it and then take the cube root. But the second you do that, you make this denominator positive. And so it's the same exact logic. The closer you get to 0, even though h is negative, this whole portion is positive. So we simply say, and of course it's as, and I guess I should have said this earlier, as h goes to 0 from the left, the h to the 2/3, okay, is positive. That's going to also 0. It's getting smaller, but it means the reciprocal of that is actually getting bigger. So in both cases, and this is why it's important, in both cases, ladies and gentlemen, it's positive. And it's really because of this 2 down here, right? And they're equal. So what this means is this limit, which is the slope of the tangent, is not finite. This is, by the way, infinite, which is not finite. Now, people say in calculus classes, well, what does this mean, Mr. Judge? I mean, you said both sided limits are the same. It's infinity, so this is my answer. Well, this is a flavor of does not exist. Because they want it to exist and be finite. So this is not satisfying the definition of being differentiable. I'll say it again. To be differentiable, right, this limit must be a finite value to say it exists. That's the definition of it. If you cannot satisfy that definition, then you can't say it's differentiable at that point. So this is a proof, since infinity is not finite, we just showed that f is not differentiable at 0. And that's the case, and that's what just happened here. So we show that this is not differentiable. This limit does not exist. It's a flavor of does not exist, but I guess you can very, very strictly logically say, in order for a function to be differentiable at a point, the definition of such, this number out here, must be a finite value, must exist. It's two-sided. Has to be finite. That's what it means to be differentiable. If you can't satisfy it, like in this case, it's not differentiable. Now, you might say, but Mr. Judge, what is this? Because, we looked at something like this the other day, and I'll tell you, yeah, we did look at it, but remember what I gave you here about a vertical tangent, right? A vertical tangent. So I'm going to say recall. Right? That's if you have that limit as x goes to a, absolute value f prime of x is infinity. And what you have seen is this here is going to be a vertical line. We'll call that a vertical tangent. You guys know from beginning algebra, what does that mean about this slope here? Right? Rise, overrun. You don't say you have a zero slope. What do you say about the slope? Right? The slope was undefined. Right? Anyway, and that's from beginning algebra language, but this is your vertical tangent concept, and that's kind of what I wanted to show you guys last time. And you can actually see a real picture. Here's a real good picture of at the origin. You're going to see here that the tangent lines there become vertical around the origin, meaning at 0, 0 vertical. But notice something, some logic. You got to be careful here. And I don't want to dirty the water here, but if it's differentiable at a point, then you guarantee it's continuous. But the converse is not valid. Here's a curve here, right? It's continuous at the origin. It's not differentiable though. So don't confuse the statements. Differentiability implies continuity, but continuity does not guarantee differentiability. This is continuous at the origin, but we just showed it's not differentiable at the origin. Deep, ladies and gentlemen. Remember that statement? And if you're differentiable at a point, then I can guarantee it's continuous at a point. Converse of the statement's not valid. Here's the converse. It's kind of like the opposite, saying the opposite statement, right? Oh, Mr. Judge, if it's continuous then it's at a point, then does that guarantee it's differentiable at a point? I go, not at all. There's a lot of counterexamples. We're looking at a lot of them today. These curves were continuous at the points, but they were not differentiable at those points. So don't read the statement backwards. Always read it forward. Okay? Anyway, that's kind of, I think, it for some of these that I wanted to do for you, because I can now get started on the second video I said I'd do for you guys. Ooh. Another video. Okay. So I'll upload this for you guys and contact you in, Canvas about it. But I hope you guys appreciated the demonstration.